Hello and welcome back to PC Retro Programmer. In today's video we're going to be drawing the Mandelbrot set in VGA mode 13H. You might know that the Mandelbrot set is a fractal image, and a very famous one at that. In fact, if you've not heard of it by name, you've almost certainly seen a picture of it somewhere. Now this might seem like a topic for an advanced video or an intermediate one, so why is it in the beginner series? Well, it turns out that VGA mode 13H is perhaps the simplest of all graphics modes. It's 1 byte per pixel, and all of the pixels are laid out linearly in video RAM, so in order to draw a pixel on the screen, all that you have to do is put the appropriate color value in the appropriate byte of video memory. That's literally all there is to it. And likewise, the Mandelbrot set is an extremely simple object. In fact, one of the earliest useful programs that I wrote as a young teenager in assembly language was a program for generating the Mandelbrot set in VGA. The Mandelbrot set is based on this very simple iteration that you see on the left-hand side of the screen here, and I'll explain exactly what this is about shortly. Now, we will need complex numbers for this, but despite the name, these are not complicated at all. In fact, the most complicated thing about the complex numbers for beginners is simply understanding what they mean. After all, they're not on the real number line, so where are they and do they even exist? But fortunately, those are questions that we don't need to answer in today's video. They're just a computational gadget for drawing the nice picture on the screen. So we don't care about all of these philosophical questions at all. In fact, the only things that we'll need to cover are how to store a complex number on the computer, how to square complex numbers, and how to add them together. And these turn out to be very simple operations indeed. So I'll begin with a very short primer on the complex numbers, and then we'll jump straight into coding up the Mandelbrot set. Now, everything we need about the complex numbers is on this page. Firstly, they're just a generalization of the ordinary real numbers. So all the usual numbers we're used to lie on this line, the real number line, 0 in the middle, positive numbers to the right, negative numbers to the left. But complex numbers are a two-dimensional generalization of this. They live in a plane, not in the line. And so this means that they have two components. One part measures how far they are in the real direction, and the other part measures how far they are in the imaginary direction, which we denote with a little symbol I for imaginary. So for example, 1 plus 2i is a complex number. That means 1 in the real direction, 2 in the imaginary direction, and then plot the point. This number has fractional parts, but this is a perfectly valid complex number, 3.1 plus 2.7i. And the reason that we call these numbers at all is it turns out we can define some arithmetic operations on them. So there's an addition of complex numbers, a subtraction, a multiplication. If you're really adventurous, you can even define division of complex numbers. And the way it works is that you just imagine that this little I is a square root of minus 1. Now, of course, there's no real number that does that, and that's why we use a little symbol for this. And basically, if you apply the usual rules of algebra, for example, expanding out brackets and so on, and this fact that I times I is minus 1, then everything will just work out. So, for example, we can use that to multiply complex numbers. Let's suppose we want to multiply a plus bi and c plus di. We'll just use the ordinary rules of algebra to expand out these brackets, and we use the fact that I times I is minus 1. So let's do that. The first thing we'd have to do is this term times this term, so that'll be AC. Then this term times this term, so that's b times d times I. And I times I is minus 1, so that must be minus BD. So that gives us the real part of the answer. And then the imaginary part of the answer just comes from the remaining products, the so-called cross terms. So we'd have BI times C is BCI, and A times DI is ADI. So this is the imaginary part. And now we have a rule for multiplying any two complex numbers. Now in our Mandelbrot iteration, there are two operations we're going to need: squaring of complex numbers and addition of complex numbers. Squaring is easy now because to square a number I just multiply it by itself, and I already know how to multiply complex numbers. Or I could just go back to first principles and expand out these brackets and simplify and use I times I as minus 1. Either way, I'm going to end up with this expression. So this is the real and imaginary part of a plus bi squared. Now the other rule we need is addition, and this is even simpler. You just add the real parts and you add the imaginary parts. So a plus c, and of course bi plus di is just b plus d times I. And so this is the real and imaginary part of the sum of these two complex numbers. Now we can also define division, but we don't need that, so I won't do it today. But there's one other thing that we need, and that's to do with the Mandelbrot set itself. So what we're going to be doing is taking points in the complex plane and applying the Mandelbrot set iteration over and over, and each time we apply it, it'll move the point about. And there's two possible things that can happen. Either the point will eventually start moving further and further from the origin and go off to infinity, never to return, or it will bounce around and it'll stay relatively close to the origin. In fact, there's a theorem that says that if it stays close to the origin, it'll never go outside a circle of radius 2. And if it does ever go outside a circle of radius 2, it will definitely go to infinity. Now, it's not a particularly easy theorem to use because, after all, we can't do an infinite number of iterations for each point to see whether or not it's going to remain in a circle forever. But what we can do is a very large number of iterations, like 100 or something like that. And if it's not gone outside of the circle of radius 2 in all of that time, then we've got a pretty good idea that it'll probably stay in the circle. And so it's probably in the Mandelbrot set. So we usually plot those points in just one color, let's say black. And any point that does eventually go outside the circle of radius 2, we plot that in a different color. Now, Mandelbrot sets typically are drawn with lots of colors, and this is just a finesse. What they do is they count the number of iterations it takes for the point to go outside the circle, and then they color the point according to the number of iterations that it took. But technically, the Mandelbrot set is just the set of points which never go outside of the circle of radius 2, and we can just use two colors for the two different cases. Now, the thing that we're going to need in order to apply this theorem, of course, is whether or not we're outside a circle of radius 2. And for that, we can just use the equation of a circle. So we take the x-coordinate and square it, and we add the y-coordinate squared. And if that value is bigger than the radius squared, which in this case will be 2 squared, then we're outside the circle. So in other words, we're going to need to look at the value a squared plus b squared, and if this is ever bigger than 2 squared, which is 4, then we know that we're outside the circle and the point wasn't in the Mandelbrot set. So we just need to keep an eye on this. We'll apply the Mandelbrot iteration over and over again, and if this value ever goes bigger than 4, we know that we're not in the set. Now, we don't really need this bit, but I wrote it anyway. This is the way that we write the distance from the origin, so this distance. And I could have written just the distance has to be bigger than 2, but then I would have needed a square root here. So this is why I used a square. Because square roots are really hard to compute on a computer. The other reason we like this expression is we already had to compute a squared and b squared up here, so we can actually reuse those values down here. So this is also very nice. Anyway, for reasons that I'm not going to go into, this whole expression here can actually be written in complex numbers as a plus bi times a minus bi. And we just use our multiplication rule. And if you multiply this out, you'll find that you just get a real number. There's no imaginary part. The cross terms in this product here cancel. A times minus bi and a times plus bi. So they cancel out. No imaginary part. This is just a real number that's left. So we just keep an eye on this. If it's bigger than 4, we're outside the circle, and that is a point that is not in the Mandelbrot set. Now getting back to our Mandelbrot set iteration, the way it works is that we pick a point C in the complex plane, and we want to know if that point is in the Mandelbrot set. So C here will be a complex number, and to find out whether it's in the set or not, we have to apply this iteration over and over again, starting from the value z equals 0. So if we plug in z equals 0 here, we get 0 squared plus c. So the first value out is just going to be c. And then for the next iteration, we plug c in, and we get c goes to c squared plus c. So that's the next value out. And then we just plug c squared plus c in for the next iteration. And so we'd square that and add c, and so on. So we just keep applying this squaring and adding c operation over and over. And if the value of z ever goes outside the circle of radius 2, we know that the value c that we started with is not in the Mandelbrot set. And we're going to colour those points according to the number of iterations that it took to go outside the circle of radius 2. And any point that doesn't go outside that circle, we're just going to colour it black. And these are the points that we think are probably in the Mandelbrot set. And so we'll get an image that looks something like the Mandelbrot set. Now, the problem with this iteration is that the Mandelbrot set lives in a box whose real part goes from -2 to 2 and whose imaginary part goes from -2 to 2. It's just a box that fits exactly around the circle of radius 2. And that's the region that we want to plot on the screen. But working with values in the range -2 to 2 is not very convenient. We'd much prefer to work with values in the range -0.5 to 0.5. They have to be signed values, of course, and we'll use 16-bit values for this. So the top bit is going to be the sign. But then basically we're going to think of these 16 bits as the bits that lie after the binary point. And so this gives us values from -0.5 to 0.5. So it'd be much nicer to work with those. And the way that we're going to accomplish this is to divide everything here through by 4. So we're actually going to use the values z on 4, z squared on 4, and c on 4. And of course we have to use a circle now of radius 0.5 instead of a circle of radius 2. So circle of radius 0.5. And the way that we're going to achieve this is we're going to use a variable capital Z, which will be equal to little z on 4. So where does this have to go to? Well, let's just try capital Z squared. So capital Z is little z on 4, and so capital Z squared is little z squared on 16. So it's not quite what we want. We have to multiply it by 4. So now we'll get little z squared on 4, and that's what we want. And I'm just going to write capital C for little c on 4. And of course, now our values are going to be in this range here. Now it turns out we can't quite represent 0.5 with this representation, but we can represent values less than 0.5. We can represent -0.5. This is just because of 2's complement representation. There's one more value that we can represent in the negative direction than in the positive direction. But this turns out not to be a major problem for our implementation.